Today we are starting the radioactivity, and we're going to start with this little accidental experiment that was performed by a scientist by the name of Henri Becquerel. Okay, and of course he's French. That's why he had this outrageous accent. Okay, and in 1896. In 1896, Henri Becquerel had some photographic film, which is the purple thing here. And he photographed film completely covered up. He wanted to use it for other purposes, and so if you photographic film, if you expose it to light, then it turns white and chemical change happens. And so he put it in the drawer, and he had the photographic film in the drawer. And into that drawer, he put a lump of uranium, which is the largest naturally occurring nucleus of any element. And he put that into the drawer and forgot about it for a while. But then when he took it out, he decided on a whim to expose it. Okay, and when he exposed the film, he found there was a big old bright spot in the middle of it. They kind of faded away as it went out from the middle. Mind you, this was kept in a dark drawer. It was wrapped in cloth in a dark drawer, so no light could possibly have gotten to this film. But the lump of uranium had been sitting on top of it, and so when he exposed the film, the uranium had been sitting right here. And he sees that this ghostly sphere, this ghostly circle, had appeared on the film, on all of the films. It wasn't just one piece of film. It went through the layers of film, and he determined there had to have been something coming from the uranium itself that exposed this film. And if it's light, that means it has to be some form of energy, or has to have enough energy coming off of it to expose the film. And with this, Henri Becquerel discovered the phenomenon of radioactivity. All right, so the uranium, these rays, whatever, these radio waves that came off of the uranium that exposed the film, he called radioactivity. And he had a close associate that he was working with by the name of Marie Curie. And Marie Curie is up there with the cosmological, the cosmic intellectual, studs of the human race. She actually has 2 Nobel Prizes. She has a Nobel Prize in physics and a Nobel Prize in chemistry for 2 entirely different things. Because she's amazing. And Marie Curie studied this concept of radioactivity, and one of the things that she won the Nobel Prize for was determining what was called this thing called radioactive decay. Okay, and the definition of this we'll give you now, although it's putting the cart ahead of the horse a little bit. Radioactive decay is the changing of a nucleus is the changing of a nucleus from one isotope to another. Okay. Now, we're not just talking isotopes of the same element. The element can actually change. Okay, and even through what is called transmutation. Okay, and the transmutation is the changing from one element to another element because the radioactive decay alters the number of protons. Okay, and this is the essence of radioactivity, is the idea of changing protons and changing the nucleus because of the instability of the nucleus. All right. So the next definition we need to get to is what radiation actually is and why radiation happens. So radiation radiation occurs due to unstable nuclei releasing energy and particles to become more stable. Okay, and this process is radioactive decay. Okay, so Marie Curie discovered the process by which particles try to become more stable, and that is called the radioactivity. That's called the radiation that's given off. Okay, so all right. So to understand then, why do things become unstable? And that's the next question that we're going to answer here: is why. Why are some nuclei, N-U-C-L-E-I, remember, unstable? Why are some nuclei unstable? Okay. So, to determine why some nuclei are unstable, we need to talk about two conflicting forces that are occurring in the nucleus. Okay. The first one is called the electrostatic force. Okay, is an electrostatic force. It is governed by a concept known as Coulomb's law. Okay, Coulomb's law is the fancy way of saying that opposites attract and like objects, like things repel. But we're going to get into the real nuts and bolts of it here in a sec. Okay, the other competing force is called the strong nuclear force. Okay, that is the competing force with it.
Is that said electrostatic?
Electrostatic, there should be an I in there.
What's the law?
Good. Coulomb's law, C-O-U-L-O-M-B. Coulomb's law. That is another French dude. Okay, so the electrostatic force is governed by Coulomb's law, and then we have the strong nuclear force. This is the actual technical name for it. It's called the strong nuclear force. It's not named after anybody. It's not very creatively named. It's just the strong nuclear force. Okay, so we're going to start with Coulomb's law. Okay, and here we have, in fact I need to zoom out. Okay. Here we have two charged particles. All right, we will call okay, that's got a positive charge on it. And that's got a positive charge on it. All right? Coulomb's law says this. as these two move closer together, okay, now first of all, they're both positive, right? Which means they're going to do what? Are they going to attract or repel? They're going to repel. Okay, so Coulomb's force says that as we bring these two objects closer together, the force pushing them apart will increase. Not only will it will increase with the square of the distance between them. Okay, so the equation looks like this. That the force, okay, and we'll call it E because it's an electrostatic force, okay, is proportional to, let's zoom in a little bit so we can see that. Okay, the force is proportional to wow, you should not be that. Okay, is proportional to Q. Q is our variable that represents charge. Okay, so if we have these charges on these two things, okay, divided by the distance between them squared. So why divided by? So think about that. If this number decreases, that's going to make this number larger, right? The smaller the denominator, the larger this force. So if we bring objects together, okay, the more they're going to push each other apart. But it's not a linear thing. It's not half the distance means twice as strong. If they're closer together by half the distance, they're 4 times as strong. If we bring them, if this right here say is 1 meter, and I bring them to 1/3, right? This isn't 3 times stronger, it's 9 times stronger. That the force increases with the inverse square of the distance. And you'll hear this term a lot. This is a future reference science term. Inverse square. Okay, Coulomb's law is an inverse square law. That means it increases with the inverse of the square of the distance. So if we double the distance, okay, it's 1/4 of the force. Yeah? Now, you've experienced this before, and I have a little demo. You guys have seen this before. Here's a magnet. Here's another magnet. These two are actually pulling on each other right now. However, the force of friction of the paper is keeping them from going like that, right? You guys have seen magnets? Yeah. Okay. So what I'm going to do here is I'm going to push them a little bit closer together. Perhaps I should do it with a non-metallic tip. Pencil. Okay. Now what do you think is going to happen? Okay. There's going to get to a point where the force of attraction between these two things is going to be greater than the friction pushing them apart, the friction holding them in place. Okay. And when that happens, they're going to get closer together. But what happens if they get closer together? Okay. Right. If they get closer together, okay, then the force increases, right? And they get closer together, and the force increases, and they get closer together. So it's an exponential occurrence that's going to slam them together. Closer, Clarice. There it was. Okay. Yeah, there's a little bit of a delay. Okay, so, but that's sort of what happens with like charges. With like charges. Now that's what like charges will do because they'll attract each other. Opposite charges repel. So, no, well, I can't demonstrate how they repel, although I can do this. I can take these two and show that. Where's my repel? There we go. if I'm going to force them together, I push them, right? And okay, I'll tell you right now, I'm already feeling them push each other apart. Okay, and I'm feeling it, and I wish you guys could see. Okay, you get this thing going on, right, where you can't. Okay, but remember the force is proportional. Is inversely proportional to the square of the distance, right? So as I get closer, it gets exponentially harder, right? So I keep bringing it together, and it's getting really hard to push them together. Okay, yeah, so they're touching. Okay, but they all right. It became significantly harder as that distance got really close. So, two things here. One, what happens if you get a positive charge? And this is a multiplier here, right? Multiply Q charge 1 times charge 2. If you have a plus times a plus, what do you get? Equals a plus. Okay. A plus charge, or a plus value here, means that as you go from this guy towards that guy, the force it's going to have is in the same direction, which would be a repel. Yeah? Does that make sense? So if we're measuring from this, to that, that's going to be, it's in the same direction, right? The push is in the same direction, so that's what the positive means. Okay. Same thing with the negative. Negative times negative is what? Positive, right? So we bring them together. This effect on that is going to push away. So a positive times a positive, or a negative times a negative, gives us a positive value, and a positive value means repel. But if we have opposites, what's a positive times a negative? Negative. So that means that the force on this guy, okay, the force there is actually in this direction, yeah? Which means it is attractive. So opposite charges attract, and that's the math behind opposites attract and like charges repel, right? This is the reason. It's this Coulomb's force. Okay. So, if these guys are protons, they're all crammed in the nucleus, right? How small is the nucleus? Really small. So these guys are just jammed in there, okay, really close together. Our D, okay, this winds up being a very small number, which makes this force really big. Yeah? There has to be something that keeps them together so that Coulomb's law doesn't rip them apart. And the thing that okay, there's neutrons. Neutrons get in there. And where's my neutron? I had a neutron lying around. Yeah, I was just kind of hanging out. Where's my neutron? Shoot, I lost my neutron. All right, I'll have to use something else. Here's my neutron. Okay, and a neutron kind of squeezes in here like that. Okay, and increases the space between them. Yeah? Okay. So that these protons aren't just crammed on top of each other. They'll never touch each other. But if we do that, okay, now there's a little bit of breathing room, and neutrons exist in the nucleus in order to allow protons to have some space in between each other, so to minimize Coulomb's law. But it's still not enough, because right now the only force that's in there is this repellent force between the protons. Yeah? We need another force. And that's where the strong nuclear force comes in. The math for strong nuclear force is heavy-duty stuff, so we don't need to cover the math for strong nuclear force. However, it is proportional, I believe, the strong nuclear force is proportional. Hold on. Proportional is. That's proportional. Okay. Strong nuclear force is proportional to d to the fourth. Huh? Okay.
What is that sign?
Proportional. Take an O and a C and crown them together, and that means proportional. I believe is it 1 over d to the fourth? Yes, it's 1 over d to the fourth. Sorry, not d to the fourth. Okay, so think about it. So if the closer the particles get, right, the repulsion is strong. Yeah? Okay, but if we get them really close together, the strong nuclear force takes over. You guys following here? The strong nuclear force takes over and grips them together. Okay, and it doesn't let them rip apart. It just grabs onto them tighter than Coulomb's law. And these are the competing forces that are going on inside the nucleus. So what do you think happens if we start adding more and more protons?
There's more and more neutrons.
Okay, right, we need more and more neutrons to space them out. Okay, but what else happens?
By the force pushing against each other is higher. C.
Okay. If the number of protons increases, in fact, don't put if, put as. Sorry, scratch it out, put as. As the number of protons increases, Coulomb's law starts to get stronger than the strong nuclear force. Okay, and the instant that happens, the moment on the periodic tables, as we're increasing our protons, we're going across the periodic table, the instant that happens is right here at number 83. This is the largest nucleus where you don't have an automatic breaking apart of the nucleus, where protons don't start ripping apart. That the Coulomb's law is not yet strong enough to break the strong nuclear force. Okay, so at atomic number 83, okay, it's the last atom to not break apart naturally. Number 84, polonium. Okay, and it's named polonium because Marie Curie was Polish, and she was the one that discovered it, so she named it after her homeland of Poland. Polonium. Sorry, Marie Curie was Polish. Oh, to break apart naturally. Polonium is the first Okay, it's the first naturally radioactive element by atomic number. It's not the first one we found, but as we increase atomic number, when we get to 84, it is a naturally occurring radioactive element. Okay, which means what? So what? So it's radioactive. What happens? Okay, either the protons start splitting apart, okay, or okay, they start shooting out of the nucleus. All right, so, I'm sorry? Okay, so they start shooting out of the nucleus. Which brings us to what the types of radiation that we have. So we have types. Yes, and notice the sparkly. Isn't that pretty? Radiation, sparkly. Okay. We have three major types of radiation. The first one has a positive charge. It is called an alpha particle. Yep. Okay, this is an alpha. Okay, it's kind of like a lowercase a with a little flag on the top. Okay, flag coming out, so it's a, all right. An alpha particle looks like this. Okay, it's got a couple of protons. Okay, with a couple of neutrons. Okay, a couple of protons, couple of neutrons. Oh, but wait a second. If it's got a couple of protons, that means it has a what? It's got a positive charge, but what do protons do? Protons give us what number? It gives us an atomic number, right? Elements are determined by how many protons they have. So if there's two protons, then that means this has to be a nucleus of some kind of element because it's got two protons. Okay, and if it's got two neutrons, right, we know that our mass number would be 1, 2, 3, 4 because it's a number of things in there, right? That's our mass number. If this is atomic number 2, we look up at our periodic table. Oh, look, atomic number 2 is helium. There are, however, no electrons around this, and so it would have a +2 charge because there's no negative charges to balance with the positive charges. It's just the nucleus of a helium atom. And that's what this winds up being, that an alpha particle is a very fast-moving okay. It is a very fast helium nucleus. This is what Rutherford was shooting at the nuclei of gold. He was shooting nuclei of helium atoms at the nuclei of gold. What do we know about the nucleus of the atom? It's really small, really dense, and positively charged, right? Okay, except this is a lot smaller than that of gold because gold has a nucleus has 79 protons and 118 neutrons-ish. Okay, so significantly larger than this dude. Okay, but they have the same density, and so this would be like throwing a baseball at a wall. All right, you throw the baseball, it's a lot smaller, you can get some good speed on it, it hits the wall, boom. Okay, if it hits the nucleus, it's bouncing off. Yeah? Okay. So, this is the first one. The purpose to the helium is to reduce okay, it is to reduce the mass and atomic number of the nucleus to a more stable element. All right, here's what that looks like. If we have Here's what the math looks like, and then we'll draw a picture. Oh, let me just flip the next page. So we'll do it there. All right. '91, '92. Okay. I didn't really count them. And 237, 238. Okay. What we've created here is a nucleus of uranium. Okay, it is uranium-238. If it is uranium, it has an atomic number of 92, which means there would be 146 neutrons. Yeah, so if you count all the reds, there's 146. For real. No, I'm kidding. Okay, this is a radioactive nucleus. 92 is greater than 83, therefore this is going to have a naturally occurring radioactive nucleus. This wants to give up. It's too big. It's just too big. 92 is just too big. It needs to get rid of some of its atomic number. So how's it going to do that? It's going to spit out an alpha particle. It spits out it spits out our alpha particle, which is a 4-2 helium. Okay, and so what's left behind? If it kicks this thing out, what's left behind? We started with 238, right? 238 protons plus neutrons, and we kick out 4 of them. What do we have left? 234 of them, right? And then over here, if 92, this is our atomic number, and with our alpha particle release, we lose 2 of our protons. How many do we have left? 90. Well, wait a second. If this is 90 protons, what do we have? What's that? We have a new element. It's a different element than what we had before. So we look in the periodic table. Number 90. Where is it? Oh, it's down. Oh, it's down the bottom. You guys probably can't see it. It is called thorium. TH, thorium. Yes, named after the Greek god or the Marvel comic book character. Okay. However, the Marvel comic book character wasn't invented yet. But the Greek god, not Greek god, gosh, Norse god thorium. This is what happens with alpha decay. Okay. All right, next one. Sometimes, if we have, now it's possible to have too many neutrons. The shape of the nucleus gets kind of funky, and sometimes it needs to rearrange what particles it has. And if we have too many neutrons, this is what happens. We get what's called beta decay. Okay, so it gives off a beta particle. That's the symbol for it. Okay, a beta particle is just that. It's an electron. It's a high-speed electron that gets ejected from the nucleus. Huh? An electron from the nucleus? What? Okay, here's what happens. This, by the way, it's just an electron. This particle has an isotope notation. What is the mass of an electron? 0, right? It's essentially 0 AMU. Okay, and that's the symbol we give it, this E minus. But if a proton has an atomic number of 1, what do you think a negatively charged electron would have? -1. The atomic number of a beta particle is -1. Mind blown, yes. This usually happens with smaller nuclei or with some nuclei that need to get a little bit bigger in order to lose another alpha particle. The most common version of beta particle that we see, that we'll be dealing with, is this reaction. Okay, so that would be that's 8 neutrons and 6 protons, which would give us 14, 6 carbon. And 14, 6 carbon splits up into an alpha particle. And what would be left? Now keep the same idea as what we did up here. If we don't lose, pardon me, if we don't lose any mass, the mass of our new particle is going to be what?
14.
It's going to be 14, right? But if we lose from the nucleus something with a negative charge, if we subtract a negative, it's the same thing as adding, right? A positive. So 6, and we subtract a -1 from it, we're actually getting a what? A 7. Oh, look, it's a new element. And atomic number 7 is nitrogen. Carbon 14, when it decays, it becomes nitrogen 14. But within the nucleus, this is the process that happens, and I need you guys to watch this very carefully. Forget about the elements. Here's what happens. 1 neutron mass of 1, atomic number 0, neutron, okay, gives off an electron, but what happened to the atomic number? This 6 went up to a 7, right? Which means if it's atomic number 7, then there has to be what? Yeah, we gained a proton, right? This is our number of protons. We had 6 before, now we have 7. We gained a proton. This is the process of a beta decay, that one of our neutrons splits into 2 different charges. The charge itself, it gets enough energy and it creates a positive and negative charge. It's like a 0 turning into a -1 and a +1 that would have normally added together. The negative one shoots out, that's the beta radiation, leaving behind a new proton, which increases our atomic number. You guys see that? Okay, that's beta particle. Now, in both of these situations, we have what's called gamma. Okay, yes, this is the stuff that Bruce Banner injected into his brain when he was trying to make himself, like, what's a canon? He was trying to make himself like Steve Rogers, okay, because he wanted to become, more Captain America-ish, and he wanted to make more superheroes, but, okay, don't do this at home. Okay, that is fiction. Okay, if you shoot yourself with gamma radiation, you'll die. Every single time. You don't become giant and green and a big old rage beast. Right? No. That only happens when you're driving. So, okay, gamma radiation, okay, is written like this. That's the symbol for it. It's a Y with a loop at the bottom. Okay, it kind of looks like this. Okay, so it's like a little wavy, particle that's pinched off at both ends. Okay, this is called a photon. It is a particle of light. Okay, you don't use these to destroy Klingons. Mixing my fictional metaphors here. Okay, with photon torpedoes. Okay, a photon is a particle of light. Okay, it is pure energy. No mass. All right, there is no isotope notation for it. It's just that, and it's just an amount of energy that's given off. Because sometimes when these decays happen, when this alpha decay happens, okay, or this beta decay happens, the nucleus is still, it's still buzzing. It's like it's had a caffeine jolt, okay, and it's buzzing. It kind of has the Beavis on sugar. Okay, the Beavis on sugar effect. Okay, and in order to calm itself down, it shoots out a gamma particle, and that's equal to the amount of energy that it needs to release in order to get back to a more stable situation. So those are our three types of radiation: alpha, beta, and gamma. Yes, they are Greek letters. I'm willing to bet the sororities do not name themselves after various types of radiation, but I could be wrong. So that is it for 25.1, and I'll be check your classroom for your homework because you do have homework tonight.